I'd like to work this example that comes from an old final exam, and it's a really great exercise in manipulating power series, which means we won't find the Maclaurin series for this by taking derivatives, for example, and evaluating the kth derivative at, well, Maclaurin would be 0 over k factorial. That's not the way we go about it. When we manipulate power series, we take a power series that we know. For instance, sine, cosine, e to the x, 1 over 1 minus x. Those power series, or the Maclaurin series for those I should say. And then we either multiply through by a power, we compose, we could add or subtract, we can integrate, differentiate. So this is the manipulation that we will practice in this exercise. Okay, well, the first thing I will do, you see, because this is built, first of all, it's a cosine of 2x, then it's a 1 minus, then we divide like this, then we will integrate. So we have a lot to do here. I will begin, let's maybe put a line under the problem, and I should say this is just part A. We will get to part B after we do part A. Okay, so let's begin with finding a power series for the cosine of 2x. I'm using this. This first step is composition. So everywhere you see an x, okay, you put in a 2x. We have k equals 0 to infinity. The coefficients remain. I see an x to the 2k. I put in 2x to the 2k. But we don't want to leave it like this. If you remember our discussion, a power series, well, centered at 0. It's of the form ck x to the k, like this, or it's a power, right? Coefficient times x to a power, which means I cannot leave it like this. So we use properties of exponents. This will be a minus 1 to the k. Well, 2 to the, well, maybe I'll write it here and I can simplify later. And then we have x to the, 2k over 2k factorial. And I will just change this box a little bit like this. What I was starting to say is this part here, 2 to the 2k, is really 4 to the k. You can put it like that, or you can leave it like this. Either one is fine. But the important part is we have coefficient times power of x. Now, you see the next thing I did to do is take 1 minus this. So I am not a write out your terms kind of person, but it might help us in figuring out what 1 minus this is. Okay, so first let's write out some terms. Well, first k equals 0. Okay. Anything to the 0 is 1. So this is 1, this is 1, x to the 0 is 1, 0 factorial is 1. Every single piece of this here when k equals 0 is 1. So we have 1. And then when k equals 1, we have a negative. This is going to be 4. This is going to be x squared over, and then we have 2 factorial. We'll have plus. This is when k equals 2. We have, this is, well, 4 squared. I'm thinking this part. We get 16. We have x to the 4th over 4 factorial. When k equals 3, we get a negative. This is 4 cubed, 64. We have x to the 6th over 6 factorial. Maybe I'll write out one more because I'm not gonna be able to keep taking 4 to these powers in my head. But the next one we would see would be a 256. And then we have x to the 8 over 8 factorial. And the next one would be negative. What happens when we take 1 minus? And this might be the trickiest part of this problem. Maybe 1 minus, well, just think about taking 1 minus big parentheses around this whole power series. 1 minus 1 is 0, okay? And then, so this first term, there is no, right? This becomes 0, but then all of the other signs, S-I-G-N, they switch. If you are negative and you take 1 minus, you become positive. If you're positive and you take 1 minus, you become negative. And similarly here, this would be a positive. And this would be a negative. Okay? Now let's write this in summation notation because, well, I find this is going to be easier for us, especially when we get ready to integrate. In summation notation, this is equal to, well, you see, everything looks the same. We have a 4 to the k, which was our 2 to the 2k. We have an x to the 2k. We have 2k factorial, right? None of that has changed. One thing has changed. No longer do we have a k equals 0 term. This was this constant 1. So our sum must start at 1. And finally, the SIGN sign has changed, okay? So if it was a minus 1 to the k, now it will be a minus, let me move this over. This was 4 to the k, x to the 2k over 2k factorial. Okay, so if it was a minus 1 to the k, now, for example, you can either write minus 1 to the k minus 1 or minus 1 to the k plus 1. It's the same thing, but we've just shifted the sign of each term by multiplying through by -1. Now, one final step, and then we will integrate. If we want the power series for this function, well, in fact, this will be my original f of x, as we will see in a moment. This is taking this and multiplying through by a power. The power is x to the -1. Now, typically, this is a problem because you know we cannot have a negative power in a power series. They don't exist in polynomials. But you see here, even looking here, right, the lowest degree we see in 1 minus cosine 2x is an x squared. So if you divide each one of these by x, or equivalently multiply through by x to the -1, we still have powers that are non-negative. Okay, so this is not problematic. Now, I will write this in summation notation. The coefficient part remains the same. So we have a 4 to the k, we have divided by 2k factorial, but the only thing that changes when we multiply through by this power is this. This is going to be an x to the 2k minus 1. And it really, I'm going to erase, maybe I'll erase this cosine. This will be my side work box for the moment. What does this really use? Well, it uses properties of exponents, which says in particular, let's say, well, I'll just do a specific example. If you add an x to the 5th over x to the 1, right? This is what I multiplied through by. Of course, there's no x to the 5th in this. I'm just showing you the property of exponents. Well, this is an x to the 5 minus 1, or x to the 4, right? So it shifts every term here. The power of x is 1 less. And that's what's represented here in this summation notation. Okay. Now, the neat thing is we built this to be 1 minus cosine 2x over x. Of course, this function on the left, as written, is not defined at 0, but the function on the right, this power series, is without a doubt defined at 0 because every power series is. Every polynomial is defined at 0. Therefore, every power series is defined at 0. And if you evaluate this at 0, well, the lowest k is k equals 1. The lowest power is x to the 1. Or you can see here, right, if you shifted all of these exponents down by 1, and then you evaluate at 0, you get 0 here. So you evaluate this power series at its center, you get 0, which is also the constant term, right? There's the constant term here is 0. So in fact, this is a power series for f of x, our original function. Maybe I should just write it that way. This is a power series here. This is a power series for our function f of x, because as I mentioned, it is defined at 0, and it agrees with f of x at 0, and it agrees with f of x when x is non-zero. Okay, so far so good, except we haven't even done part A yet. Part A, we need to find the antiderivative. Well, let's erase. This is what we want, right? Well, it's c plus, we recopy everything except I'm going to leave off this part. Oops, sorry about that. I'm going to leave off this part. The part I have dotted underneath in red is the only part that has x to a power. Everything else is a constant with respect to x, what we're adding here, but I mean this part is a constant with respect to x. Okay, so let's write all of this. It's a minus 1 to the k. We have 4 to the k over. We have 2k. Uh-oh, I miscopied. K minus 1. 4 to the k over 2k factorial. K goes from 1 to infinity. Okay, so far so good. I have copied the constants. And then, while we integrate, this is a power of x. We add a power, divide by the higher power. So here we go. We add 1 to this. It is the x to the 2k over 2k. Okay? So this is part A. This is the power series, Maclaurin series, because you see it's centered at 0 for the antiderivative here. It's how we built it. Now part B, it says, what degree 4 polynomial best approximates this, the integral from 0 to x of f of t dt for x near 0? Well, you see we already have an antiderivative here. We have this capital F plus c, if you think fundamental theorem of calculus. Okay, so what would we do to answer this question? Well, if you have a capital F, you don't need the plus c. You would just evaluate at the upper limit, evaluate at the lower limit, take the difference. Right, well, we have this capital F, and we've already, well, you can see, you evaluate this capital F at 0. What do you get? Here, the lowest power is squared. This has no constant term. So you evaluate at 0, you get 0, right? So in a sense, the only thing I need is look at this antiderivative, okay? And then what is its degree 4 polynomial part, which means we add up all the terms until we see an x to the 4th, and that will be the highest one that we use. Okay, so here we go. Let's start writing out terms. What's when k equals 0? Okay. Oh, excuse me. There is no k equals 0. K equals 1. This is the first term we see in the sum. Okay. Well, it was good you saw that because I was going to write down the term for k equals 0. I looked up my sum started at k equals 1. It's important to start where your sum actually starts. Okay. My k equals 1 term. I have minus 1, well, to the 0. Then what do I have? I have a 4 to the 1 over 2 factorial, and then I have an x squared over 2. Okay, I will simplify this in my next step. Right now, I am just writing out terms. I will keep marching forward through k until I see an x to the power of 4. This will tell me, oh, I've hit degree 4, and then I stop. Okay, here we go. K equals 2. Well, minus 1 to the 2 minus 1, this will be a negative. Then I have 4 squared, which is 16. I have divided by 4 factorial. That's this first part. Then I have x to the 4th, and then over 2 times 2, 4. Well, I've already found something of degree 4. Okay, so this polynomial will be the best approximate. Best approximates this. Yes, very good. And like I was saying, if you wanted to think about evaluate the upper limit, evaluate the lower limit, take the difference, technically, this would be with respect to t. Then you would put 0 to x. Like this. Evaluate at x, you get exactly this. Minus. Evaluate at 0, you get 0. Okay, so this would be our degree 4 polynomial. And now, what is this? Well, this is 2 times 2. 4 over 4 is 1, so we have x squared. Now, if we make a little side box for the coefficient in front of x to the 4th, we see we could write it this way. 4 times 4 over 4 factorial times 4. These 4's will cancel. 4 over 4 factorial is 1 over 3 factorial, which is 1 over 6. So this is a little side work box. My coefficient here is 1 over 6. So this is 1 over 6 x to the 4th. And this is the final answer for B. This is the answer for B. Okay?